So in the last class we saw about the uh, discrete time LTI systems, and we also saw that how to compute the response of a system for any arbitrary sequence by using the convolution operation. So today we shall see the properties of discrete time LTI system. So since LTI systems are described by the convolution sum, like we saw in the last class, the properties of this class of systems are also defined by the properties of discrete time convolution. Meaning to say, so the output of the system y of n is given by the convolution of the input signal or the input sequence convolved with the impulse response of the system. So the first property says that I can also compute the output by having the convolution of Hn convolved with Xn. So you can recall this property from your signals and systems class, and you can derive this property by yourselves. So if we just one point to see here, so the first part was equal, if I put as a summation, so it was from k minus infinity to infinity x of k hn minus k for all values of n. So the second one will read as k from minus infinity to infinity hk and xn minus k. So this is what we mean, that these two computations would remain the same, which you are seeing on the right hand side. Okay, so the second property is that it distributes over addition. Meaning to say that if we have an impulse response of the system defined by the summation of two individual systems, which we can write as h1 of n plus h2 of n. So if I convolve this system by the input sequence x of n, then I can write as x of n convolution with h1 of n plus x of n convolution with h2 of n. So you can see in this form that I have, in the block diagram form, that I have h1 of n, the impulse response of the system 1, the impulse response of the system 2, so these are in parallel. You see, similar. So you would have y of n, and the input signal is x of n. So this part corresponds to this part, and this part corresponds to this part. So if we add these two convolutions, we would get y of n as the summation of their individual responses. The next property is the associative property. Which says that if I have a system which is the convolution of two different systems, that is h1n and h2n, h1 of n convolved with h2 of n, then the convolution of this system with x of n it can be associative in the sense that first I can compute x of n convolved with h1 of n, and then its convolution with the h2 of n. So from the block diagram representation, this means that two systems having their impulse responses h1 and h2 of n respectively can be connected in the cascaded form. X of n, and this is my y of n. Okay, and since it is from the first property, which is basically this one, I can redraw this block diagram as h2 of n convolved with h1 of n. Again, it will give me the same response for the same input. Okay. So both of them is basically can be written as h1 of n convolved with h2 of n, or h2 of n convolved with h1 of n. Okay, so these are the three important properties which can be applied to analyze the properties of the discrete time LTI systems in general. Now in the last class we have also studied about the Bibo stability, and we have defined the Bibo stability in terms of the bounded input signals and the bounded output signals. So if we want to map that conditions onto the impulse response of the system, we shall see that now. So we have this Bibo stability. So we say, okay, so we got interrupted a bit. So we were discussing about the Bibo stability in terms of the impulse response of the system. So the LTI system is Bibo stable. LTI system is Bibo stable if and only if we have the following condition, that there exists some finite number bh, which is computed by taking the summation of mod of h of k, where h is the impulse response of the system for k ranging from minus infinity to infinity, and it should be a finite number, right? You can also see this property that the impulse response of the system is absolutely summable. Okay, so this is again a necessary and sufficient condition. So we can see that how it becomes a necessary and sufficient condition. We can see a very quick proof for this condition for checking the stability or Bibo stability of a discrete time LTI system. So first of all, let's write this, your y of n, which we have seen earlier, can be written as k from minus infinity to infinity hk x n minus k. Okay. Now taking the summation both sides, the modulus both sides, we can write this as the right hand side would be less than or equal to their individual modulus of the term, which is mod of h of k and mod of x n minus k. Okay. Now if x of n is bounded, that is your x of n is less than or equal to some finite number b of x, then the above expression can be simplified to mod of y of n would be less than or equal to bx bh, because this condition strengthifies this expression on the right hand side. Okay. So if we have bh less than infinity, then your mod of Eigen would also be a finite number, because bx is already a finite. So this is the proof for the sufficiency, that bh less than infinity implies that your LTI system is b-bow stable. Okay, so for the necessary condition, we shall show that if you won't have bh less than infinity, then it also implies that your LTI system is not b-bow stable. Okay, so if, of course, for some bounded input. So now to prove the necessary condition, first of all we need a bounded input. Let's define one bounded input x of n as for hn not equal to 0, and it is 0 when you have hn is equal to 0. So this is some bounded some input sequence which you can verify that it is always bounded, since x of n is less than equal to 1, where your h star of n is the complex conjugate of your h of n. Okay, so once again let's write the output response y, and we are interested in computing the value at n is equal to 0. Okay, so y of 0 can be written as minus k to minus infinity to infinity as x n minus k. So n is 0, so it would be only minus k and hk. Right, now substituting x of n from here to here, you will get summation over k hk modulus square divided by hk mod, right, which in fact is some number b of h. Right? So for example, if the summation of h of k ranging for k minus infinity to infinity, there is some number b of h. So at y is equal to 0, if your bh is not a finite number, so it could only be a infinite number, then your bounded input does not give you a bounded output. And this is what we wanted to show, that your bounded input does not give you the bounded output. Right, so this is the proof of the necessary that why this condition is necessary also. Another is of the causality, where we saw that the output sequence should depend only on the past and the present value of the input sequence. Now in terms of the impulse response, that your h of n should be equal to 0 for all n less than 0. Right? So if the impulse response satisfies this property, then we say that the system is a causal system. Right? So moving ahead, now we have been talking about the LTI systems and seeing the properties of the LTI system. Now we will see that how those LTI systems can be represented mathematically. Okay, so we use the linear constant coefficient difference equation. Okay, so using these difference equations, we represent or we formulate the LTI systems, and they can be generally represented as k equals 0 to capital N, k y n minus k equal to capital N dn xn minus 1. So if you recall the system equations from your signal and system class when you studied for the continuous time case, so there we have the linear constant coefficient differential equation, but in the discrete time we have the difference equation which are represented by this. So if you recall that we have been considering some specific types of system in the previous class, so one of the example we have considered majorly is the accumulator, and it is defined by y of n is equal to summation of k minus infinity to infinity x of k. Excuse me, it should be up to n. Okay, so let's see how we can represent this accumulator system into the above form. So taking the nth element from the right hand side, I can write this equation as y of n as x of n plus the rest of the part k minus infinity to n minus 1 x of k. Okay, now see this, that it can be written as yn minus 1. So you would have yn minus y of n minus 1 is equal to x of n. Right? Now if you see the similarity between this difference equation and this difference equation, you can obtain this directly by substituting n is equal to 1, a naught is equal to 1, a1 is equal to minus 1, and on the right hand side m is equal to 0 and b naught is equal to 1. Right? So if I substitute this entire part here, you will get this equation, this difference equation, which of the accumulator. Okay, and if we see in terms of the block diagram, I would have this y of n, it is a summation block and it goes to xn. So this is your yn minus 1, where to this system which is one sample delay. So one sample delay system where the input is y of n and it is delayed by one sample gives yn minus 1, which finally adds up with xn to yield yn. Okay, and in generally also we can represent this y of n from this equation. That again, if I take the this expression for k is equal to 0 outside of this summation, I would get y of n. Okay, so it can be generically represented as y of n, and taking the rest of the part from the left hand side to the right hand side, I will have from k is equal to 1 up to n all a k's divided by a naught yn minus k plus k is equal to 0 to n bk by a naught xn minus k. So this would be my generic representation of this thing. So now the solution, the interesting part is you can solve the system of equations by in a classical way, where you represent or where you compute the overall solution of the system as the homogeneous solution and the transient solution by TR. Okay, so this you can read it as the steady state solution, and this is the transient solution, transient state solution. Okay. Now this is what we have, how we have been how do we generally do for the continuous time case when we solve the differential equation. But since these are the difference equation, you can solve them recursively also, where you don't need to compute this steady state and the transient solution, but recursively you can compute, like in one of the examples we had seen in the last class. when we represented the summation of the a to the power k as a geometric sum. Okay, so one specific case we can see that if you have capital N is equal to 0 in the above uh, difference equation, then you will see that this part would no longer be there for n is equal to 0. Then in that case your Yn would be equal to k is equal to 0 to m bk by a naught xn minus k. Now if I set xn as equal to delta of n as an impulse input, then I would get an impulse response of the system as h of n, which would be equal to summation k is equal to 0 to m bk by a naught delta of n minus k. Okay, and another way of representing is that I have bk by a naught for all n lying between 0 to n and 0 otherwise. Okay, because saying this limit and this delta. So such kind of systems we call the FIR systems, finite impulse response system. So finite impulse response system, where the impulse function takes finite number of values, like in this case that it is only defined for 0 between 0 to m, otherwise it is 0. So all these systems are called the finite impulse response systems. So there are other class of system which are infinite impulse response, so we will see such kind of systems also. Okay, IIR systems and FIR systems. Now let's see the frequency domain representation of discrete time. Discrete time, signals and systems. Okay, so the one important property which is associated with the frequency domain representation, that given any LTI system, if I give the input to this discrete time LTI system or continuous time LTI system as the complex exponential or sinusoidal signal, then I will get the output of the system same as the complex exponential signal or sinusoidal signal. So there are two important points to note, that the output of this LTI system will have the same frequency as the input signal. Okay, but the output signal might be changed in the amplitude and the phase. Okay, it might be different from the input signal, and these two things, amplitude and phase, are determined by the system, but the behavior of the signal would remain the same. Okay, now let's first of all see the definition of an eigenfunction. So an eigenfunction of an operator, let's call a hat, is a function, let's say f, So f is an eigenfunction of an operator a hat such that the application of a hat on f gives f again times a constant. Okay, this we can see mathematically. This a hat, if is applied on f, where f is an eigenfunction, such that the application of a hat on f gives f again multiplied by a constant. Let's call it k. So this k is generally defined as the eigenvalue, and this f is your eigenfunction, right? So if you can recall from your mathematics class that you have studied these in terms of matrices, where if you have a square matrix A applied on a vector x, then you wrote it as lambda times of that vector x, where lambda is your eigenvalue and x is your eigenvector. Okay, so now the question arises, why are we discussing these two eigenvalues or eigenfunction for the frequency domain representation? So the point is, let's say if we talk about the LTI system once again, having an impulse response h of n. Now in frequency domain, I can represent this in this form, where we have h of e to the power j omega, which you can compute by from k minus infinity to infinity, hk e to the power minus j omega k. Okay, so this is in the frequency domain representation, and which you generally compute by the Fourier transform. So we will talk about these Fourier transforms and inverse Fourier transform and a couple of properties of those systems. Okay, now if I apply the input x of n to the system whose impulse response is h of n, and let's say this input is your complex exponential e to the power j omega, where you have n from minus infinity to infinity, then you can write your y of n as h e to the power j omega times e to the power j omega n. Now if you see the analogy between the definition of eigenvalues and eigenfunctions, so you will quickly notice that this is your eigenfunction and this represents your eigenvalue. Okay, and they both are of course the function of frequency. Okay, so if you consider a input sequence at some particular frequency omega, then your output signal would be of the same frequency, but there would be a change in the amplitude in the phase. So you can represent that y of n by this, and for some frequency this would be your eigenfunction and this would be the eigenvalue at that frequency omega. Okay. So we can stop here.